things that are just falling, okay? Not anything that's thrown or anything like that, but things that are just dropped, okay? So a free-falling object is still considered constant acceleration, because when I have an object in free fall, do you know what the value of its acceleration is? What is it that's pulling it downward? Gravity. Okay, so there is an acceleration that's due to gravity itself, and that's a constant value. Okay, that's a value that we're going to learn and you'll start being really familiar with. But when we fall, we're moving at a constant acceleration. So that doesn't mean we're moving at a constant velocity. It means we're moving at a constant acceleration, right? We're increasing our speed at the same rate the whole time that we drop. Okay, so that's a little bit of a different concept, but we're going to do a problem today that I think will help see that, okay? What do you think about this? Do heavier objects fall faster than lighter objects? Yes or no? Do heavier objects fall faster than lighter objects, given that they're the same shape? Yeah, your slide says no, right? Okay, it seems intuitive to think, yeah, a heavier object's going to fall faster than a lighter object, but the reality is that that's not true. It has to do only with their shape and the amount of surface area that interacts with the drag force or the air resistance force in the air, right? So if you drop a piece of paper that's crumpled up versus a piece of paper that's flat, which one do you think is going to hit the ground first? Crumpled up, right? Because not as much of that paper is interacting with the air as it falls. But a crumpled up piece of paper that's the same size as a tennis ball, if you drop them both, they'll hit the ground at the same time, right? Even though the tennis ball is heavier. So we're going to watch a little video that is, I don't know, so bad it's funny, I guess. Yeah, about how this kind of first came about, so.
Is to make college easier, because
if that's true, I want you to look at your kinematics equation. So go ahead and grab your equation sheet out if you don't have that yet. Look at your kinematics equations. We use the same set of equations for horizontal and vertical objects. Does mass go into our equations anywhere? No, right? We never put mass into the equation, which just shows us, again, like there's no reason that heavier objects would fall differently than lighter objects. All right, so when we're talking about objects that are moving vertically or in free fall, so anytime an object is in free fall, that means it has nothing connected to it, right? It's just freely falling through the air, or it hasn't reached the point in which its connector has been extended, right? So let's say like you're bungee jumping. You're free falling until that bungee catches you, right? Once the bungee catches you, then you're no longer free falling, but when you're moving through the air without anything propelling you upward or downward, you're considered free falling. So during that time, you undergo what something is called acceleration due to gravity. Acceleration due to gravity, or we just keep it as an A, okay? Some books you'll see maybe put it as a G, a little g for gravity, acceleration due to gravity, but we'll just keep it as an A. And we know if it's vertical, it's got a certain... it has a certain value, and that value for vertical acceleration is negative 9.8 meters per second squared. Okay, negative 9.8 meters per second squared. Is that a value that seems familiar to you? Have you heard that one? Okay, gravity is negative 9.8 meters per second squared. And in all reality, what is the negative really just telling us here? Yeah, it's moving downward, that the acceleration is in the negative direction. So we need to understand that regardless of if my object is moving upward or downward, it still has an acceleration of negative 9.8 meters per second. Because as my object moves upward, let's say I launch something straight up into the air, is it speeding up or is it slowing down as it goes upward? It's slowing down, right? As things reach its highest point, what happens at an object's highest point? It stops, right? When it reaches its highest point, it stops, and then it starts to fall down. So let's think about our rule of thumb for acceleration. My object's moving upward and slowing down, which means my acceleration should be negative, right? And as I'm moving downward, I'm speeding up. So I'm moving downward, I've got negative velocity, and I've got negative acceleration. So the acceleration due to gravity is always negative 9.8, regardless of if my object is moving up or down.
So when an object is moving up, is there any point in which it is launched that it is speeding up and then starts to slow down?
Yeah. The very beginning of that motion, it might still be speeding up, but the acceleration is still negative 9.8. It's still causing that object to start slowing down. Yeah, good question.
Is that something that we should put on our...
You can put on your equation sheet if you want. We're going to use it so much that you'll have it memorized, but if you want to put it on there, you can.
But, and this is only for...
This is for vertical kinematics, for objects that are moving vertically.
If it's going up, is it still moving negative?
Yes. Acceleration is negative 9.8, regardless of the direction of my object. Okay? So if we're free falling, we've got constant acceleration in the y direction. That's the reason we can use our kinematics equations, right? Because we have constant acceleration, and that acceleration is due to gravity, so negative 9.8. Okay, if you like to rewrite the equations with y variables, you can. I'm going to leave that up to you. So what that means is that our equations will look the same, except we'll have y instead of x. Okay, so my velocity final equation still looks the same, vi plus at, right? Because it's still just velocity. You could put a y there if you want, right? If you want to add another little subscript there, you could. You don't have to, but the second equation might change because it would say y final equals y initial plus vit plus 1/2 at squared. And then the third one would be vf squared equals vi squared plus 2a y final minus y initial. So if you feel more comfortable having a different set of equations for y versus x, you could put that on your equation sheet. I'm going to leave that totally up to you. Okay, I do make the change when we're talking about vertical. I use that y variable. It's not like I'm always going to use x. Okay, I use x when we're talking about horizontal, y when we're talking about vertical. If you really wanted to, you could even change the a to a g, so you would remember that it's gravity, but I usually don't do that. I usually just keep it as an a. So if you want to keep yours how I do them, I kind of usually keep it at an a there, and I just know that when I'm vertical, I will start using negative 9.8 there. Okay. When we start looking at situations in which objects are moving in both directions, horizontally and vertically, we will go ahead and add a y and an x into those velocity variables, but we don't need to do that quite yet. Okay. So as we start looking at these equations, I want us to really be thinking about how we write correct answers here. So when we're talking about things that move forward or backward, it's very clear to us whether our answer should come out positive or negative, and mathematically it almost always does that. Okay, in these situations, you might have to end up adding a negative to indicate that our object moved up or down, or that it ends up moving in the negative direction, especially on this third equation here. Okay, because let's say I was solving for velocity final. What happens in my calculator when I take the square root of something? Does it come out positive or negative in my calculator? It comes out positive, but in all reality, what's the actual answer to that square root problem? Right? If I take the square root of 16, what's the actual answer to that problem? Okay, it's plus or minus 4, right? Because either of those gives me a positive 16 to take the square root of. So when I use this equation right here, I've got to really be thinking about, if I'm solving for VF and I take the square root of that, I have to think about, should my velocity be positive or negative? And I might have to add that negative there. Because if I did this problem and my object was moving down, my answer would have ended up being negative 4 meters per second. Right? That's just something I want us to be thinking about as we're working through this. Okay? Let's go ahead and try one here. All right, suppose that a ball is dropped from a tower 70 meters high. How far will it have fallen after 1, 2, and 3 seconds? Okay, it asks us for 3 different things here. This is not a problem we do in one shot, right? We're going to actually do the problem 3 times here. And this is to really demonstrate to us the whole kind of phenomenon of acceleration. So I want us to kind of look at this one carefully. So here is I'm going to draw my 70-meter tower. All right, here's my little guy up here at the top. There's the ball. Okay, I guess the ball needs to be at the height of the tower, but whatever. Okay, we're essentially right here, 70 meters. Now, what did I say about where the origin goes? Where do I like to put the origin? I like to put the origin here, okay, at the start of my motion, or at 70 meters high. Okay, you could choose to put the origin at the ground, but that would mean my initial position is 70, right? And what do I like my initial position to be? I prefer that my initial position is always 0. Okay, so that's the reason I like to put the origin where my motion starts from, so that in this case, my y initial is 0. Does that kind of make sense? If you chose the origin to be at the ground, then your y initial would be 70, right? Because you would be starting 70 meters above that. Okay, so that's not my preference, but it works the same. Okay, mathematically it works the same. So let's go ahead and start looking at this. If I am looking for how far it has fallen, that means I must be solving for y final. Right? How far it's fallen has to be y final. I know my initial position is 0. What do I know about my acceleration? Negative 9.8. And was that given to us in the problem? No, so that's a variable that you have to be able to just know, right? Especially when you know it's a vertical problem, you've got to be able to just know that A is equal to negative 9.8. Okay, and when it says my ball is dropped, what does that tell me about my initial velocity?
0.
It is 0, okay? So the second that ball leaves my hands, right? The second that my hand becomes detached from that ball, it's still not in motion yet, right? It's 0 meters per second until gravity can start pulling it into motion. Now, that's a really, really tiny millisecond that it's at 0. But in all reality, for the second my hand becomes detached, my initial velocity is 0. If it would have said I threw the ball, then I would have had an initial velocity of whatever it said I threw it at, right? But dropped means my initial velocity is 0. Okay, then it says after 1 second. That's what we're going to try here. So t equals 1. Okay, that's all the variables we have. We can't worry about the 2 and the 3 seconds right now, right? Those are the only variables we have. So what equation could I use if I want to solve for y final? First, second, or third? Second. I agree, second. Okay, so let's go ahead and use the second equation. Y final equals y initial plus vi times t plus 1/2 a times t squared. Right? Having an initial velocity of 0 really makes this equation very easy, right? You can drop out really those first 2 terms because initial velocity times time is still 0. All right, go ahead and grab your calculator if you don't have it yet. So really I'm taking 1/2 times negative 9.8 times 1, which means my y final is negative 4.9 meters. So what does it mean here that my final displacement is negative? Right, it's okay, so I want to rephrase that just a little bit. I'm ending up 4.9 meters below where I started, right? Because it's a displacement, the negative tells me I'm 4.9 meters below where I started. So after 1 second, I'm about there, right? After 1 second, my ball might be about there. It might even be a little bit farther up. I'm not great at drawing that to scale, but...
It would just be negative 9.8 because if you're going 1 second, is that not?
Right, so it says after, with every second that goes by, my velocity increases 9.8 meters per second. So my velocity here would be 9.8, but it doesn't mean that I've traveled that many meters yet because I started from 0. Okay, so now let's do the same thing after 2 seconds. Okay, after 2 seconds, can I just use the same equation and all I need to do is change my time, right? Yeah. Right, I don't need to even worry about what happens after 1. I'm just going to start again from 0 and see where I'm at after 2 seconds. So y final equals 0 plus 1/2 negative 9.8 times 2 squared. So y final equals negative 19.6 meters. Are you surprised that we're not just double the distance from our first part? Right? We shouldn't be surprised here because of that square. Right? We're not falling at constant velocity. Our object is speeding up as it falls. Right? With every second that goes by, my velocity is increasing by 9.8. So I'm covering more ground with every second that goes by. So now after 2 seconds, I've fallen to a total distance of 19.6 meters. So this might be after 2 seconds, I'm right there. right? You see how the gap after each second's getting a little bit bigger, right? I've traveled that long, then I've traveled that far after 2, right? With every second that goes by, I'm going to cover more and more ground. That's what acceleration is. Okay, so let's try after 3 seconds here. Okay, negative 44.1 meters. So here I'm probably, I don't know, somewhere around there after 3 seconds. Right? So with every second that goes by, I've covered more and more ground. Okay?
Will you ever have
All right, suppose the ball from the last problem was thrown downward with an initial velocity of 3 meters per second instead of being dropped. What would its position be after 2 seconds? Okay. So after dropping the ball, our position after 2 seconds was 19.6 meters below. Would you expect it to have fallen farther or less distance if it was thrown downward? Farther, right? We're going to expect that number to be greater than 19.6. So let's go ahead and see what our variables are here. So what's the variable that's changing? Initial velocity. And so is it positive 3 or negative 3? It's thrown downward. So we have to read our context clues. Negative 3. Okay, let me just show you this real quickly. Okay, here's my cliff. Here's my ball. It's thrown downward. Okay, my equation could do the work if it had been thrown upward, and it would have done all the work for me. If my object has been thrown upward and we wanted to find its position after 2 seconds, my equation still does all the work for me, knowing that my object was going up to begin with and my acceleration is negative. It does all of that for me, but that's not the case here. Okay, so even if it was thrown upward, my velocity would go in as positive. My equation would do all that work for me. To understand, it would go up and stop and then come back down, right? My equation does all that for me, but that wasn't the case here, so... my y final is what I'm solving for. Y initial is 0. Acceleration is negative 9.8. And time is 2 seconds. Okay, so we're still going to use our second equation, right? Y final equals 0. But this time we're not dropping out that initial velocity. We've got to take VI times T plus 1/2 A T squared. And so I get a Y final here of negative 25.6 meters. Okay, so if we're answering what would its position be after 2 seconds, I would take this answer, or you could say it's 25.6 meters below, or if you really wanted to, actually this is probably the best 2 ways. If you really wanted to, if you had started with 70 as my initial position, it would have been 70 minus 25.6, but I don't usually answer questions that way. Okay, so we throw the ball upward, right? Here's we want to figure out how high it goes and how long the ball is in the air total. Okay, so here's what I want to think about first. Let's go ahead and calculate how high it goes. That's the first thing. So what portion of the motion are we looking at? The whole thing or just the first half of the motion? Just the first half. We're just looking at this section right here on the way up, right? So we're looking for Y final at this point, right? How high it goes. So Y final is our question mark. Our initial velocity here is 15. And is it positive or negative? Positive, because we threw it upward. My acceleration is negative 9.8, right? Regardless of if my object is going up or down, my acceleration is negative 9.8. Okay, I don't know anything about time, so I can't plug that into my equation. What do I know about my object at this point? It's stopped. which means at this point, my final velocity is 0. Okay, so in these vertical problems, we have to be able to kind of partition out our problems a little bit and think about, okay, for this portion of my question, I'm really only envisioning the first half of my motion, from my hand to its peak height. Okay, you'll hear me say peak height a lot. You know what that means? Its highest point, right? That's what that means. So from my hand to its peak height is the only portion of the motion that I'm examining. And so I've got a velocity of 15 meters per second, and then at its peak height, it stops, right? That's a concept we really got to be comfortable with, is that at its highest point, it stops for just a second before it starts to fall again. So this does not mean it's moving at 0 meters per second when it hits my hand again. It means it's moving at 0 meters per second right here, right, at its highest point. So what equation could I use here to solve for YF? I had to use the third one because I don't have anything about time, right? And time is left out of the third equation. So I'm going to use that one. That one is VF squared equals VI squared plus 2 times A times Y final. And it's Y final minus Y initial, but we know Y initial is 0. So do we need to bother putting that in?
Wouldn't it be -2?
Which one?
You have that.
This equation would normally look like change in Y, right? Which is the same as Y final minus Y initial. So if I'm solving for Y final minus Y initial, but I know Y initial is 0, I don't really need to bother putting that into the equation at all. We can just say I'm solving for YF. Okay? So 15 squared is 225 plus negative and 19.6 YF equals 0. Then mathematically, what do I need to do here? Yeah, good. I need to move 225 to the other side, and then I'll divide that by negative 19.6. And so I get a Y final of 11.48 meters. And it came out positive. Does that make sense that it comes out positive here? Yeah, because I threw my ball upward, right? So it makes sense that my displacement is above, or it's positive from where I started, right? Because the origin was right here where my motion began from. Okay, so my Y final was 11.48 meters. Okay, now to solve for time, there's two different ways we can do this. The first would be to take into consideration the whole entire picture of the motion, all the way up, all the way down. But I'm going to show you what I think is a quicker way to solve for time and will be a little bit more applicable to us as we move forward. And that's this. If I throw my ball into the air, straight up, straight back down, that motion is perfectly symmetrical.
So I have to do which ones?
Yes, but just hold on. Okay, when I throw the ball straight up into the air and come straight back down, it's perfectly symmetrical motion, which means it takes the same amount of time to go up as it does to come down. Are we agreeing with that? Does that make sense to us? Okay, when I throw something into the air, it's going to take exactly the same amount of time to go up as it does to come down. Because on its way up, it's slowing down. And on its way down, it's speeding back up. Okay, so it's going to take exactly the same amount of time. Which means I can solve for how long it takes me to reach peak height and then just multiply that time by 2. Okay, the other alternative is to solve using the second kinematics equation and say Y final equals 0, Y initial equals 0, plus 15 times t plus 1/2 a t squared. Oh, shoot. Do you see a problem with this? Solving this equation? I have a t and a t squared, which means I have to do what? I have to use the quadratic formula. Okay? So we'll get to that eventually, but until we have to use that, I don't want to use it. Okay? So when my motion is non-symmetrical, I have to go about this way. But when my motion is symmetrical, I can use what I call the shortcut method and just solve for the time it takes to reach peak height and then multiply it by 2 because it's going to take the same amount of time to come down. Yeah.
So when it goes up and it comes back down, is the velocity the same?
Bingo. Yeah, but in the negative direction.
So it'd be negative.
So my final velocity at my hand, when it reaches my hand again, should be negative 15. Yeah, and we could do it, the problem to see it mathematically, but yes, it will be. Good question. Okay, so let's go ahead and solve for time then to peak height. So now at peak height, I know my initial velocity was 15, this was this. Is my velocity still 0 at peak height? Yeah, right? So I'm going to use that portion of the motion. I can just use my first kinematics equation, the easiest one. Velocity final equals velocity initial plus A times T. So I take 15 divided by negative 15 divided by negative 9.8, and I get a time of 1.53 seconds. But is that my total time? No, since I said VF was 0, that's only the time to its peak height, so I have to multiply that by 2. Okay, which means I think it took me a total of 3.06 seconds. Okay, for it to come up and then hit my hand again. So this method, this shortcut method, like I like to call it, only works when my motion is completely symmetrical. Completely symmetrical. Starts and ends at the same height. That's what we mean by symmetrical. Let's say that I'd done this. Let's say that I had started the motion here at my hand, and I threw the ball upward and let it hit the ground. Is that now symmetrical? No. So in that situation, I'd have to use like the quadratic to end up solving for that. But we'll work our way through there. Okay? Does that make sense? Because here it's not symmetrical. It fell farther on the way down than it did on the way up. Okay? Or it traveled farther on the way down than it did on the way up. Okay? So we'll look at that kind of more specifically when we get to projectile motion. But another example of where that might be the case is that, let's say I'm on a cliff again, right? I don't know how often this happens, but in physics, we like to think it happens a lot. I throw the ball into the air and then it lands on the ground. That's also non-symmetrical motion, right? So you can either solve it in two equations. Like you could solve how long did it take to reach this height, and then how long did it take to fall that height, and you could add them together. That would work too instead of doing the quadratic. So there's just a couple things you can think of there. Right? There's always more than one way to get to our final answer with kinematics equations. It's just about what set of equations you want to use, right? You could use the second one and the quadratic, or you could do two different ones with time. But it's really about the problem solving and being able to think about, these are the portions of my motion I have to solve, and then how do I put those together? Okay?